Okay. So, last time we were discussing the spectral analysis. We defined what is called power spectral density. Of course, we are dealing with this continuous systems. We are dealing with continuous systems, analog systems. So, we just start from there once again, it will help us. So, suppose there is a analog random process, analog or continuous time. So, I just today I put a subscript A just to denote there is an analog signal XAT, let it be a random process, analog random process, and it has a correlation R A say T, R A tau, which is okay. And what is the power spectral density here? Phi A j omega is equal to maybe I change the notation a little here. So, I put R x x here. It is assumed, since I will be dealing with only continuous time case or analog cases only. So, even if I put R x x and do not mention any A here, it is assumed that I am still considering an analog or that is continuous time random process. So, similarly, here phi x x j omega, which we know is a Fourier transform of the autocorrelation function R x x tau, that is e to the power minus j omega tau d tau minus infinity to infinity. We have seen that even though the random process is complex valued and therefore, the correlation is a complex valued function, the power spectral density is a real valued function. Okay. And if the process is in fact real valued, then the power spectral density is not only real valued, it is also an even function. In fact, it is a non-negative function which we will show today. Then last time I was considering towards the end of last day's lecture, I was considering an analog system, linear time invariant system with impulse response to HAT. Input was a process XAT, output is a process YAT. First we saw that the output also is WSS if the input is WSS, and then we found out the output power spectral density. I just repeat it today in case there was some confusion left that time, that will clear up. That is what we do now is that we have got a process XAT, it is inputted to our analog system is HAT, this is the impulse response. Once again I put a subscript A here to indicate there is it is an analog system. HAT is the impulse response and output is a random process YAT. YAT is given by the analog convolution between these two XAT and HAT, we all know. So, this is YAT, which you can write either way, maybe you write this way XAT minus tau d tau minus infinity infinity. So, what is the output mean if input is stationary? Now, if what is the output mean YAT, that is you can take the expectation operator inside the integral, because expectation is a linear operator, and then HA tau is not random. So, E operator will work directly on XAT minus tau and minus infinity infinity HA tau, E working on XAT minus tau d tau. But I told you that input process, that is XAT is WSS. So, therefore, its mean is constant independent of the time whether it is t or tau or t minus tau, and you can call this thing as then mu x can go outside the integral. So, you get again a constant, okay, which is independent of any time t, you can call that constant mu y. So, output mean also is constant independent of time. So, it is proved that is first order stationary. We will now see the case of output correlation, again that will be function of only that we will see that is a function of only the lag, and therefore, it will show that it will prove that output also is WSS. We did it last time, so I am going a little fast here. This is pretty straightforward. In fact, this whole derivation is pretty mechanical, so you can afford to go fast. Okay. E double integral YT, H tau x t minus tau, this is with respect to tau, okay, and then h say tau prime x, sorry, tau is already, tau cannot be used, I am sorry, tau is already used outside. So, this cannot be tau. Tau is already a constant r y y tau. So, I cannot use tau as an integration variable. Okay. So, let me call it, let me make it T 1 d T 1 and T 2. This is y star. So, that means h star x star T minus tau minus T 2 d T 2. And then E will work directly on the product between x t minus T 1 and x star T minus tau minus T 2, because other quantities, that is h T 1 and h star T 2, they are not random. So, what you get, and I can push the E operator inside the integral using the linearity of expectation operator. Okay. So, what you can do is this, you have got h T 1 h star T 2 and then E working on x t minus T 1 into x star T minus tau minus T 2, this is d T 1, this is d T 2. Now, you see this quantity is given, is the autocorrelation function. Okay. And since input x at is WSS, the autocorrelation or correlation will depend only on the lag between the two time points. One time point is t minus T 1, another time index is instance is t minus tau minus T 2. So, it is nothing but r x x tau plus T 2 minus T 1. And now, you see, if you integrate the entire thing with respect to T 1 and T 2 and get the result, all T 1, T 2 disappear, everything, then the final result becomes just a function of tau. So, that means the autocorrelation function, as we wrote in the beginning, as a function of tau, is indeed a function of tau. So, there is lag, it is indeed a function of lag only. So, this proves that output is WSS if input is WSS, and input signal is passed through LTI system, input is WSS, output also is WSS. The moment we say that output is a WSS function, WSS signal, immediately the question comes as to what is the power spectral density of the output then. That means, we have to find out the Fourier transform, analog Fourier transform of r y y tau, and there this expression will come handy, this integral. So, I will just keep it here. Okay. So, what is phi y y j omega? It is nothing but r y y tau e to the power minus j omega tau d tau minus infinity infinity. There is a Fourier transform of output autocorrelation. R y y tau we have just evaluated just a while back, this is given by this bottom expression. Okay. So, this have to r y y tau has to be replaced by this. So, we basically have triple integral, and you know these triple integrals, if each of the integral, even though indefinite integral, because limits are from minus infinity to infinity, but if we assume that each integral is converging, that exists, in that case the integrals can be interchanged, okay, like interchanging double or triple summations, you know, provided each sum converges, they can be interchanged. And we are assuming that we are dealing with functions where all the integrals are converging and all that. So, we are not looking for those exceptional cases. So, in that case, I can interchange the integrals, and then what we have, there is the integral with respect to tau will be the innermost integral. Okay. First, you replace r y tau by these two. So, there are two inner integrals, one with respect to T 1, another with respect to T 2. Then I interchange the integrals, the integral which was outside so long, which was the outermost so long, that is with respect to tau, that becomes the innermost. Okay. I am leaving a gap deliberately, you will see why, and then the inner integral r x x tau plus T 2 minus T 1, then e to the power minus j omega tau d tau. This I write as e to the power minus j omega, not just tau, but I bring in those two T 2 minus T 1. So, obviously, you have to cancel out those extra terms that I have brought in. One is e to the power minus j omega T 2. So, therefore, I have to have e to the power plus j omega T 2, which I bring in here, and another term is e to the power plus j omega T 1. So, I should have e to the power minus j omega T 1. Okay. First one is obviously analog Fourier transform of H, which is the frequency response of the system. Second one, you can take the star out from here, put a minus, and the entire integral you can bring a star on. So, this is nothing but H star j omega. And here tau plus T 2 minus T 1 can be called tau prime. Okay, everything else remains same. So, this becomes the Fourier transform of R x x tau prime, which is nothing but input power spectral density phi x x j omega. Okay. I remember last time I did it in a hurry, and in fact, I should not or okay, that is why I am doing it again. Now, remember one thing, I am writing phi y y j omega. In fact, it will be better if I remove j, because these are all real functions, there is no place of j there. So, permit me to remove the j from here. Initially, I put a j because I was carrying out Fourier transform, and normally when you take a time function and take a Fourier transform, the Fourier transform is denoted as a function of j omega. So, keeping that in mind, I put a j, but now I know that power spectral density is a real function. So, there is no point in keeping the j there. So, I remove the j. Similarly, from here also. Okay. So, you see input power spectral density is multiplied by the mod square of the or that is the magnitude square of the frequency response. So, you can design a system where for certain frequencies the magnitude may be high of the transfer function or the frequency response, and in certain other frequencies magnitude may be less, and therefore, at certain frequencies you can boost up the power spectral density, and at certain other frequencies you can suppress. So, you can give a shape to the input power spectral density, which gives rise to the idea of filtering. That is, you can generate a function whose power spectral density is mostly a low pass type, okay, which is, that is, if you plot it versus omega, you get its function having non-zero appreciable values only around omega equal to 0, close to, and as you go far away from origin, it becomes less and less. That kind of signal is called low pass, opposite of it is called high pass, and all that which you know. So, all this can be obtained by just designing for a given specified phi x x omega. You can just design a filter to have a output power spectral density of some specified shape. This gives rise to the idea of filtering. Okay. This I will now use to show that any power spectral density is not only a real function, it is also a non-negative function. Okay. That is, to show this, what I do, let x a t pass through a system h a t. X a t can be complex valued, h a t can be complex valued, but remember, if you call the output y a t, then power spectral density of input, that is x a t, or power spectral density of output, that is y a t, they will always remain real, irrespective of whether x a t is complex, h a t is complex, or y a t is complex. Okay. Now, I design the system h a t such that it is just a band pass filter, very narrow pass band. I am not showing it to be that narrow here, but actually very narrow, infinitesimally small bandwidth, center frequency is some omega naught, sorry. Capital omega is my notation for analog frequency, that is radian per second. So, center frequency is omega naught and this bandwidth is say delta omega. Okay, this is my H A j omega. Obviously, H A t in this case is complex, because as you can see H A j omega is just one sided. I do not have a similar thing on the left hand side, and therefore, if you take the Fourier transform, it will be complex value. So, H A t is complex value here, but I do not care. Okay. What is that is simply height may be equal to 1 into, we have just seen this theory few minutes back, we have in fact proved it. Okay. Now, what is R y y 0, that is autocorrelation at lag 0? We have seen that this is given by 1 by 2 pi minus infinity to infinity phi y y omega d omega. In fact, that is why this is called power spectral density. Quickly, how just to recall how it comes, we have seen that power spectral density is the Fourier transform of autocorrelation function. So, therefore, autocorrelation function or maybe correlation function here, okay, is the inverse Fourier transform of power spectral density. So, if in the inverse Fourier transform R y y tau, if you put tau equal to 0, then e to the power 0 is 1. So, you get this integral only, which also shows how, okay, shows that the power, average power R y y 0, average power of the process is given by the integral, that is the area under the power spectral density. So, by looking at the power spectral density function, we can see which part of the power spectral density function contributes most to this area and which less, and thereby, okay, you get to know, okay, how is the average power distributed along the frequency axis, where it is high, where it is low. That is the reason why it is called power spectral density function. That is beside the point, we have already discussed it last time. Now, R y y 0, you all know that it is greater than or equal to 0, because it is, what is R y y 0? It is nothing but E mod y t square variance. That can never be negative, that is real and non-negative. Okay. Now, in this case, what is R y y 0? I have to integrate phi y I omega from minus infinity to infinity, but there is no point in integrating from minus infinity to infinity, because it is 0 everywhere, because input power spectral density, whatever it is, that is multiplied by this narrow band pass filter. So, output power spectral density will be confined only around omega naught within this band of delta omega, elsewhere it will be 0, because H a j omega, its magnitude is 0. Okay, you can even take it, call it with the magnitude. Okay. So, therefore, what I have to do, if the suppose input power spectral density is like this, some function, then at what is approximately the area? Area will be I mean, if delta omega is very small, you can take the center, I mean, value of phi x x omega at the center point, that is phi x x omega naught. You can assume that to be constant over this zone of delta omega, because delta omega is very small. So, whatever be the value at the center frequency omega naught for input power spectral density, you can take that to be flat, because delta omega is very small. Okay. So, in that case, very simply this product, if you take the product and then compute the area, that area will be what? Phi x x omega naught into 1, because this height is 1, into, that is this height, into delta omega. Okay. Phi x x omega naught in delta omega, that is the area, and multiplied by 1 by 2 pi, and this is greater than or equal to 0. Now, delta omega is always positive, this only shows phi x x omega naught is greater than 0, greater than or equal to 0, but we chose omega naught purely arbitrarily. So, this is true for any omega naught. If you ask me to, okay, you ask for phi x x omega at any omega naught, I can design a band pass filter with center frequency at that omega naught and do the proof, and it obviously shows that power spectral density at that omega naught is greater than or equal to 0. So, it is a non-negative function, is proved. Another thing I forgot to mention is the concept of white process. There is one class of random process which is called white process. In fact, you come across this term in the context of communication, where you deal with a noise called additive white noise. Okay. White process is where the signal is absolutely uncorrelated, that is, say r x x tau, its value is non-zero only when tau is 0 and other is 0. That is, if you take two samples, however close they are, their correlation is 0. Only when tau is 0, that is the sample, I mean you take it on itself and then find the correlation, which in fact gives rise to variance, then it has got some value. So, it is basically n into some delta tau, where delta tau is the so called Dirac delta function or impulse function, unit impulse function. Okay. This kind of process is called white process. In this case, power spectral density, why white, you will see, will be what? If you take the Fourier transform, you basically get n delta tau e to the power minus j omega tau integral, that will be 1. Okay. This is n, which is constant independent of frequency. So, it is flat, that is why it is called white, that is all frequencies are present with same I mean power. It is like white light, it consists of so many frequencies in uniform proportion. Okay. That is why it is called white noise. Okay. Okay. I will consider one or two examples of how to compute power spectral density and all that for the analog case, but before that let me now consider discrete sequences, random sequences, and a similar treatment is valid there also. Let me complete that part first, and then if time permits I will come back to this example, otherwise I will take up this example in the next class. Okay. Discrete, that is, so long as dealing with analog, that is why I was putting a subscript A. Now, I will be dealing with sequences, that is discrete random signals. Here I am giving x n, where n is an integer. So, I have got a sequence x 0, x 1, x 2, this is random sequence. Here correlation r, okay, x x, say k is an integer, is what? Okay, just a minute. Give me a minute. This is. I hope you didn't get distracted. Anyway, this is a function of k, because this is WSS. Okay. This is a WSS process. So, because I will follow, I mean I will carry out the same treatment and same interpretations will follow. So, let me not spend too much time on this. I will take the just discrete time Fourier transform. You know, this is a sequence. So, here the Fourier transform will be not the analog Fourier transform, but DTFT, discrete time Fourier transform, and that is your phi x x, and instead of writing as a function of j capital omega, it is a function of j small omega. Small omega is the digital frequency, its unit is just radian. I could have called, in fact, I should have, I can write it as a function of just small omega, but again, you know, I follow the convention in DSP. They write DTFT as function of e to the power j small omega, though E and J are constant, they are not variable, only omega is variable, but it is written in the same in this way, so that you can easily differentiate it, distinguish this, differentiate it from analog Fourier transforms, and also it always reminds us that this DTFT is actually a power series in e to the power j omega. After all, what is DTFT? DTFT is this is the formula given r x x k. If you take its DTFT, it is this. So, it is actually a power series of e to the power j omega, k from minus infinity to infinity. Okay. Then what is r x x k? It is the inverse DTFT. Similar treatment, you see, minus pi to pi. Remember DTFT, this is periodic. I mean, this is part of DSP. I presume that you already know it, but in case you do not know, please see certain things. What is the unit of omega? After all, omega into k has to be an angle radian. K is just integer dimensionless, which means omega has to be radian. Omega is called digital frequency. What is the relation with analog frequency capital omega? We will come to that later. It is just omega radian. And one more thing, if instead of omega, you can see I replace omega by say omega plus 2 pi. What do I get? I get one term as e to the power minus j omega k as it is. What is the? I get another term e to the power minus j 2 pi k. Now, e to the power j 2 pi k or e to the power minus j 2 pi k is always 1. That is, if you take any angle 2 pi and take any integral multiple of that in the positive or negative direction and take e to the power of that is always 1. E to the power j 2 pi is 1, e to the power j 4 pi is 1, e to the power j 6 pi is 1, e to the power minus j 2 pi is 1, so on and so forth. So, that means, if you replace omega by omega plus 2 pi, still you get the same expression. That is, this is same as e to the power j omega plus 2 pi. If that be so, that means this function is a periodic function of omega over a period 2 pi. So, it is enough that we plot it from 0 to 2 pi or minus pi to pi. I prefer minus pi to pi, and whatever you see there, that just gets repeated. Okay. These are all facts from DSP, but in case you do not know, it is worth mentioning here. Coming back to RxXK, this is called inverse DTFT relation. I suggest that in case you do not know, please read the first chapter of OpenMC's first DSP book. Okay. Read the topic of discrete time Fourier transform. The inverse Fourier transform, this is lot easier than analog, by the way. What is the inverse DTFT? This is given by this omega k d omega. So, you want to find out the autocorrelation function at an index k. So, you carry out the integral with respect to omega, you bring in the same k here inside. This also means Rxx0, that is E of mod xn square, which is Rxx0, that is nothing but e to the power j omega 0, because k is 0 here, that is 1, and therefore, you get just this integral. Same interpretation follows. D omega. So, you see phi xx e to the power j omega is such a function of omega, which when integrated from minus pi to pi, then that integral, that is the area under this function phi xx from minus pi to pi, that gives you average power. That is why it is called power spectral density, in the same way as phi xx j capital omega was called the power spectral density of the analog signal xat earlier. Same treatment. I am just giving the new definitions, that is all. Physical interpretations and all, they remain same. Okay. As before, this is again a real function, same derivation, same proof, similar proof, only integrals are to be replaced by this discrete sums, that is take k equal to 0 out separately, Rxx0. Rxx0 is what? Irrespective of whether xn is a complex valued process or real valued process, Rxx0 is, as seen above, is the variance E of mod xn square, that is E of xn into x star n minus 0, lag 0, the autocorrelation for lag 0, which is always a real quantity. So, Rxx0, and then other summation, here it was from minus infinity to infinity. You can take this way, one summation from k equal to 1 to infinity, another part is k equal to minus 1 to minus infinity, same thing. Now, here k, if you replace k by minus k, then what is the, firstly what happens to the summation indices? K by say minus k prime, in case you can get confused, k by minus k prime say to start with. That means, when k is minus 1, k prime is 1, and when k is minus infinity, k prime is infinity. So, summation ranges from 1 to infinity, Rxx minus k prime e to the power plus j omega k prime, and now call k prime as k, and two summations can be combined into one because limits are same. plus r x x minus k e to the power j omega k. Now, remember one thing, I am doing it separately here. Do you remember r x x k, what was it? E of x n x star n minus k, right? This according to me is also r x x star minus k. Why? First, what is r x x minus k? You have got x star n plus k x n, okay. And then if you take star over it, the star star cancels, and a star comes on x n. So, you have x of n plus k into x star n. N plus k if you call n 1, it becomes x n 1 x star n 1 minus k, expected value of that, which is again r x x k. That means, what is r x x minus k? This is nothing but r x x star plus k. So, you see whatever you have here, these two, one is the conjugate of the other, r x x k, r x x star k, it is the power minus j omega k, it is the plus j omega k. So, real number z, sorry, a complex number z and its conjugate, summation will be real, and r x x 0, the outside quantity is also real. So, overall is real. Okay, so, real function. And once again you can see this response of linear systems and all that, we can do it very quickly. Suppose x n goes through h n, this is a linear shift invariant system, we get y n. Y n is nothing but the discrete convolution h r x a n minus r from in general minus infinity to infinity. So, what is E y n? Input is W s s. E will go inside working on, it will work directly on x into E of x n minus r, input is W s s. So, expected value of any sample of x, be it of n minus r, sample at n minus r, that is constant, that we can call mu x. So, this summation is again a constant independent of n. So, you can call it mu y, which is independent of n. So, that means output mean is constant. So, in the output is stationary in the first order, we will see that output is stationary in the second order also. Treatments you can see is absolutely similar to what we had there. What is E of y n? Y n is what? This is y n into y star n minus k, y star n minus k. Y star means h star have a separate variable name, this is r, all from minus infinity to infinity, y n and then y star n minus k, is not it? Y star n minus k means convolution evaluated at not at n, but n minus k. So, n minus k minus m star, because it was y star. Actually, I am skipping one step, because I now assume that you yourself can work out that step. Okay. The first summation gives y n, second summation gives y star n minus k, you can verify, I suppose. And then E will work directly on wherever you have x and x star and all that. So, push E inside using the linearity of E, h r okay. Sorry. And then you have got E working on this x n minus r into x star n minus k minus m. Input is W s s. So, this autocorrelation will be a function only of the lag. Lag is what? N minus r minus within bracket n minus k minus m, which is r Okay. And you see, if you carry out the whole summation, m and r disappears, everything becomes a function of just k. So, output correlation is indeed a function of k. So, this proves that output also is WSS. Obviously, this leads to the following question: if it is WSS, then what is power spectral density? Fine, so we have to take this Fourier transform. So, I remove this intermediate step now. I take the Fourier transform, this is over k. So, that means this entire thing has to be summed multiplied by this entire thing has to be multiplied with square minus j omega k and summed over k. That sum over k will be the outer sum, but I can interchange the sum, make it the innermost sum j omega, just a minute, j omega k, but instead of writing k, I call it k plus m minus r. So, I brought some extra term, they have to be cancelled. So, I should have e to the power plus j omega m that I write here, and I should have e to the power minus j omega r that I write here. First quantity is obviously the frequency response dTFT of h n, there is a frequency response. Second quantity you can take the star out. So, e to the power minus j omega m it becomes. Okay. You can easily see that this is nothing but h star e to the power j omega, and here k plus m minus r can be called k 1, everything else remains same. So, this is the dTFT of discrete time Fourier transform of r x x k or r x x k prime rather, which is the input power spectral density, which is phi x x e to the power j omega. So, again I get that filtering expression h square. Okay. This is a discrete time version of that previous equation. Okay. Again using this, you can show that phi x x e to the power j omega also is a, but it is not only a real function, it is a non-negative function. How? This time we will just consider this, and h e to the power j omega. I will not prove it, which is again a band pass filter. The range is from minus pi to pi. This is band pass filter centered at say some omega naught of with delta omega. Okay. If x n is passed through this, if you know in x n is complex valued, and of course, h n is complex valued, y n is complex valued, but the power spectral densities are real, that we have already seen. And what is the output power spectral density? That will be given by this previous this thing mod h to the power j omega square phi x x to the power j omega. So, what is r y y 0 as before? This will be integral of output power spectral density from minus pi to pi multiplied by 2 pi, minus pi to pi phi y y e to the power j omega d small omega e to the power j small omega, but this integral is localized only around omega naught within a band of delta omega. Okay. And filter height is say 1. So, it is a question of finding the value of input power spectral density at the center point omega naught, assume that remains constant or flat over the entire band, because band is infinitely small. So, overall area becomes nothing but 1 by 2 pi times phi x x e to the power j omega naught times delta omega, and this must be greater than equal to 0, which means power spectral density is non-negative function. Okay. So on and so forth. And like analog case, here also you can define white sequence. Okay. If r x x k, which is nothing but if it is some constant say n times delta, and this delta is not Dirac delta function, it is just a sequence, it is called unit impulse sequence delta k. What is delta k? delta k equal to 1 if k equal to 0, else equal to 0. That means x n is uncorrelated with any sample, any of its neighbors, far away or nearby ones. And when k is 0, R x is 0, which is the variance, variance is given by capital N, because delta 0 is 1. Okay. For such a process, the power spectral density phi x x e to the power j omega, obviously if you do the DTFT you can see it is constant n, so it is flat, that is why it is called white. Fine. Now, suppose why, I mean actually now it will be clear as to why I suddenly went for discrete sequences. First, suppose that we have got an analog function x a t, analog random sequence x a t, and you are sampling it, sampling at period, sampling period equal to say t, to get a sequence x n. So, if x a t is random, x n also is random. From a random continuous valued or analog signal, by sampling I generate a random sequence x n. So, what is x n? That is n t, nth sample. Okay, sampling period is capital T. So, one sample is taken at t equal to 0, another is capital T, then 2 t, 3 t, 4 t. So, nth sample, that is x n, is nth sample of, that is the value of this function x a t at what time point? At n into capital T. Fine. So, that means what is R x x k? Whenever I write R x x k, you look at what I write inside. It is k, k stands for integer, then that means I am talking of the random sequence, its correlation function. If I write R x x tau, then I am not talking of the autocorrelation function for any random sequence, but autocorrelation function of a continuous valued, that is analog sequence function, because tau is random. Okay. Now, what is R x x k? It is E of x n x star n minus k, which is equivalent to E of x a n t into x star a n t minus k t, which is equivalent to R. Maybe if you permit me, to avoid confusion here, I remove this subscript R, this x x, just R k, and this is R a. R a stands for the correlation function for the analog function. When there is no subscript, then it is the correlation function for the random sequence. So, R k, and since I am dealing with no other person, no other sequence, no other function rather than x, let us drop the subscript related to x. This R k, which is this E of x a n t into x a star n t minus k t, that is if you call k t to be tau. So, this is nothing but R a at a lag of tau, that is k t. What does it mean? It means that I am given a function R a tau as function of tau, autocorrelation function, okay, some autocorrelation function R a tau. I am taking the samples at 0, at t, at 2 t, at 3 t, at minus t, like that. Okay. So, I am getting these things. This is R 0, this is R 1, R 2, sorry, this is R 1, R 2, R 3, R 0, R minus 1, so on and so forth. So, this autocorrelation sequence R k is actually obtained by sampling the corresponding analog autocorrelation function at a sampling period of capital T. Okay. You know, it is very much like sampling a continuous time signal. We have studied Nyquist sampling rate theory and all that. That time a continuous time signal is sampled with sampling period capital T, you get a sequence. Okay. we find out the DTFT expression for the sequence and relate it to the analog Fourier transform of the analog function, and then you get an expression and then find out when aliasing will occur, when aliasing will not occur and all that. Okay, same thing we can do here. So, what we are given here is this, that this sequence R n is a sampled version of an analog autocorrelation function R a tau. It is just sampled at a sampling rate of 1 by t or sampling period of capital T, and you get this sequence. So, if your phi e to the power j omega is and phi a, now I am writing, because I am again dropping the subscript related to x, phi a j capital omega, this is the analog Fourier transform of then what is the relation between phi e to the power j omega and phi a j omega. You can see one thing, that R n is given by the inverse DTFT of phi e to the power j omega, that is in fact R n the inverse DTFT relation, and R a n t, these two are, remember these two are equivalent. This is given by inverse DTFT of not inverse DTFT, inverse analog Fourier transform of the corresponding analog power spectral density. But evaluated at a time not any tau, but specifically n into t. Now, the two left hand sides are equal, that you have seen. So, that means by equating the two right hand sides, we can try to derive a relation between the two power spectral densities. One of them is a discrete one of them is a PSD for the discrete sequence, another is the PSD for the analog, the original analog random process. Okay. Now, the second integral you can break down like this whole interval from minus infinity to infinity, you break like this, you take the gap, one thing from pi by t to minus pi by t, then take another range from pi by t to 3 pi by t, another range from minus pi to minus 3 by t, like that, dot 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 dot. Okay. So, instead of integrating once for all from minus infinity to infinity, I want to break down the integral over non-overlapping sectors. One sector is a 0th sector, this is 0th, this is first. Okay. So, basically rth sector will be where? So, 0th sector center is at 0, first sector center is at 2 pi by t, second sector center is at 4 pi by t. So, rth sector center will be at 2 pi into r by t. So, that range will be 2 pi r by t plus pi by t minus pi by t. Okay, and that r will continue from minus infinity to infinity. Do you understand what I am saying? I am dividing the entire range of the integral minus infinity to infinity into, I am doing the integral as a summation of sub integrals, and sub integrals are finite sub integrals. Okay, one will be from range minus pi by t to pi by t, that I will call 0th. Then next one will be from pi by t to 3 pi by t, that will call first. Next will be 3 pi by t to 5 pi by t, that will call second, so on and so forth. What is the rth? Rth will be what? How to identify quickly? For the 0th, the center was 0. For the first, center was at 2 pi by t. For the second, center is at 4 pi by t. For the rth, it will be 2 pi r by t. So, 2 pi by r by t, and then further pi by t to the right and pi by t to the left. There is the rth, and now take r equal to 0, r equal to 1, r equal to 2, r equal to minus 1, all that, the r minus infinity to infinity. So, the entire range will be covered. So, that is what I do. this entire integral will be written like this, sub integrals from 2 r pi by t minus pi by t, that is 2 r minus 1 pi by t okay. Whenever you come across double summations and assuming the summations exist, they can be interchanged. Okay. That is what I would do here, but problem is the inner summation has got r in the limit and outer summation is over r. So, these two cannot be interchanged, that is inner summation cannot be over r. So, r is finished and still you find an outer summation, there is integral where r comes in the limit. So, for that matter what I have to do, I do not know whether in 5 minutes I can complete it, but I will carry on in the next class. Anyway, let me see as much as I can. Okay. So, what I do, I need about 7 minutes to complete it, not 5. Anyway, so what I will be doing, I will be shifting the origin, that is earlier origin was here, and what is the rth integral was, rth zone was here, 2 pi r t. So, I will be shifting the origin here. That means, for this particular integral I will replace omega by omega prime, where omega prime is omega minus 2 pi r by t. In that case, if I make the substitution, what all we get? Actually, what I am doing is always done in DSP, while proving Nyquist theorem. So, there is nothing new, but still I am doing it. So, in that case, what will be the integration limits? When omega becomes 2 pi r by t plus pi by t, omega prime goes to plus pi by t and minus pi by t here for the lower case. Okay. And d omega prime are same. Okay. So, I make these changes here. So, what I get, phi a so I said omega prime equal to omega minus 2 pi by r t. So, that means this becomes j omega prime plus j 2 pi by t, okay, into e to the power, this is interesting, j, what is omega? Again omega prime plus 2 pi r by t into n t d omega prime. Now, you see the second factor 2 pi r by t into n t, t cancels, I to the power, I need 5 minutes, e to the power j 2 pi r n equal to 1, okay, e to the power j 2 pi r n, that is equal to 1. So, it makes no difference actually. Okay. So, I can always rewrite this like this, and why again omega prime, bring back our good old omega. So, you call it omega, sorry. Okay. And there is a t here, of course, omega n t. Now, if you have small omega equal to capital omega t, then d omega is 1 by t, d omega is d capital omega. Okay. And what happens to this integral? This becomes, and I interchange the two summations. Now, I can easily interchange because r is disappeared from the integral limits. So, r and I put a 1 by t here, because 1 by t d omega into e to the power j omega n d omega. This quantity I will take up in the next class again. This quantity will give you this, if you compare the two integrals, and the limits, sorry, I made a mistake, the limits will not be from minus pi by 2 t, it will be from minus pi to pi, because if capital omega is pi by t, product is pi, if capital omega is minus pi by t, product is minus pi. So, integral limits are from minus pi to pi. Okay. So, you see the two integrals are identical. So, you can easily find out what is phi e to the power j omega. Okay, and the relation between analog and digital frequencies is omega, this small omega equal to capital omega t. Now, this I will give a physical interpretation of this, and I will see that by Nyquist condition you can avoid aliasing, and therefore, if you have aliasing, you can get analog, you can get the analog this thing, I mean power spectral density directly from digital, the power spectral density of the sequence, which you obtain by sampling the analog random function. Okay. In that case, if your purpose is to estimate the power spectral density of an analog signal, it is better you sample it at above Nyquist rate, there is no aliasing, and find out by some computer algorithm, sophisticated algorithm, the power spectral density of the corresponding sequence or n, x n. Okay. From that, you can easily construct phi a j omega. So, I will start from here in the next class. Thank you very much. Last class we are doing one thing in a hurry. So, maybe I just start from that and do it again. That is, suppose there is a random continuous value, that is analog random process x a t, okay. This is sampled at a time period, sampling period of capital T to generate a sequence x n. So, obviously, x n also is a random sequence. So, you have x n equal to the nth sample. That is, if you sample at t equal to 0, then small t equal to capital T, then twice t, 3 t, so on and so forth. The nth sample, I call it x n.